Okay, recording will start soon. Yeah, there we go. And then I want to share a screen. All right. Is that the right one? I think so. So okay, you can see things?
Yep.
Yes.
Yes.
Okay. All right, so let's begin. Today, I want to continue. This just lists where all the subjects we got to, and with the lectures, well, rather with the description so far, it's been quite numerical oriented in the last couple of lectures, and so I wanted to give some insight from a different point of view. So if we remember from last time, what we were doing was showing numerical solutions to very simple, this is an isothermal atmosphere, and it showed very specific properties. And so to remind you, we have a two-level atom, so the source function is just 1 minus epsilon J plus epsilon B, and J is the angle average of the mean intensity. And so we're looking at kind of classical quantities here, but now we're going to start thinking about photons and where they come from. So moving from a classical back to a quantum kind of picture. And the epsilon is the amount of real thermal emission we have in a given spectral line. Using a two-level atom is a great tutorial thing, but it's more than that too, because the rate of transfer in one line is pretty much the one thing that controls the relative populations, which is the source function. Rate of transfer in all the other lines certainly affect that, and in the continua, but it still contains the physics of the basic physics of how photons interact with the gas. So this value of epsilon tells me how strongly is the radiation coupled to the atmosphere or the plasma. And this is an atmosphere which is infinitely deep. So log tau on the right-hand side goes up to whatever the sun's center is. So there's really, that's a local thermodynamic equilibrium. That flat line at the top means that the photon movements are sufficiently local that everything looks to be governed by the epsilon, the collisions. So we've collisionally coupled very strongly electrons with the atoms with the photons. So there are two aspects that we found when we looked at this dependence. One is that you get more and more nLTE as you have less and less coupling, which is exactly what we'd expect. But we haven't coupled this, say, to the coronal approximation, even though it's still the same transfer equation. Now, but the two facts I want to take from this are, if you look at the values of epsilon and you take the square root of them, that's where the left-hand side joins the axis on the left-hand side. Well, that's telling us that the source function at the surface is the square root of epsilon times b, whereas where it joins the horizontal line at the top, namely when it becomes thermalized, when it becomes isotropized, when it becomes relaxed to a fully LTE state, that's what we call a thermalization length. And there are two parameters, two things that emerged from this, which is one is the square root of epsilon time, one of them is the square root of epsilon time b is the source at the surface. And then it merges into B, whatever B is. So if we had a multi-temperature structure and it was a curve or a steep gradient or something, they would still tend to approach B when the total optical depth on the x-axis is about 1 over epsilon. So this governs the global transport of the numerical calculations. The question is, why does it have to really behave like this? Is there something we can learn here? And what we're going to do today is look at photons briefly and ask questions about how the photons move in space and in frequency and in angle, and see how it relates to this kind of stuff so we can get a feeling for this. Otherwise, we end up just accepting these things, and we don't really, I don't personally remember scaling laws like this very well. I happen to remember this one, unless I have an understanding of it. So there's the surface value, and that's what we're talking about, is this. If we can get those two things right somehow in a heuristic model, then we have the way, we know something about the way in which the radiation affects the source function. And in fact, from the source function is all we need if we use something like the Eddington-Barbier relation to tell us what the profile should look like. So we know, for instance, that all these are going to show a variation in the depth of a line formed in an isothermal atmosphere, such that if it's strongly coupled to the gas, the radiation, it's a very shallow line. But if it's very very weakly coupled, then there's the scattering somehow. The rate of transfer makes the core very, very dark indeed. Okay. So let's just remember some of this analytic stuff that we looked at. So there's the basic transfer equation, and there's a cos theta term on the left-hand side, which is represented by mu in a 1D atmosphere. So this is just the slant angle at which the ray you're going through, tracked by d tau, is. All right. So we integrate that one over mu equals cos theta, and we end up, because we integrate I over all mu, and on the left-hand side, we end up with an integral over mu squared, and on the right-hand side, with an integral over just over mu. Sorry, we have an integral over mu on the left-hand side and just an integral of I without any mu in it. There's no moment there. So we end up with two moments of the angular moments, J and H, out of this thing. And this should, if this is familiar, so let's have a quick look at this one. This one will be particularly interesting as we go forward. This is saying that the derivative of the radiative flux is whatever the solution to the equation of transfer is, J, averaged over minus the source function. And in radiative equilibrium, we know that dH by d tau by definition is zero. There's no gradient in the flux, and that's exactly a thing that the sun is doing at its surface, or rather that's an approximation. We have convective transport, but when the radiative transport dominates, then we know that J has roughly got to be equal to S, or rather accurately. And if we just sort of write down an integral for that at the bottom there, we see that we haven't learned very much by writing the integral of J minus S d tau, but we will shortly. But that's also equal to minus J times the absorption rate per centimeter plus the local emission. And if now that gives us a clue as to how we might connect this thing to, say, the corona, because if we have tau is very small, and if we have a J that's very, very small as well, so it's 10 to the minus 6 of the brightness of the sun, the corona, something like that. And if we integrate down onto the solar disk, where the emergent radiation in the EUV is very, very tiny, then we get H equals the integral of epsilon dz, and that's just the integral of the thermal emission. That's very familiar. That's what the coronal approximation, well, part of the beginning of the coronal approximation is. Whatever, so you're just integrating conservation of radiative energy. That's all it is. But that's the coronal approximation. There's the link there. So that's the first little bit of insight. So far, we've been thinking in really classical terms of moments of the transfer equation, source functions, and J. But here, we're going to look at some considerations of photons. We're going to look at escape of photons, some analytic work. We're going to become a little bit familiar with various things that you'll find in terms of the literature, which go back, I think, 50, 60 years, when we have something called radiative detail balance, which is on the spot. Core saturation is absorption on the spot. We'll get to this shortly. But and when I was putting this together, I thought, what is the best way to do this? And I reread Sharma's 1981 paper. That's a typo there. The paper that he wrote, Yaron Sharma, in 1981 for his PhD. Okay, and it turned out that this has such beautiful explanations in a simple way. You'll forgive me if I cut and paste and just guide you through a couple of paragraphs of his, because it shows the genius of someone who can see right through to the basis of how physics relates to numerics, how you can understand the numerics in the basis of physics approximately, and then develop analytical tools with certain approximations to be able to implement them in the numerics. This paper basically sort of started to revolutionize rate of transfer when it was written in 1981. Okay, so as I said, if you'll forgive me, there's the correct, this is his entire PhD thesis. It is 11 pages long. It's in two parts. The first part is the one we'll talk about today. The second part is what I talked about last week, which is the accelerated lambda iteration method. So I've got a little bit out of order, but there's a reason for that. And I hope that it works out okay, sort of in terms of explaining how to understand things. So there's a picture of Yaron Sharma. When he did his thesis, apparently he had long hair. Everybody thought he wasn't getting anywhere. He did it part of his thesis work at HAO, amazingly enough. So what was he doing? Well, we look at a two-level atom, and this is basically written in terms of the equation number 2. So what are we looking at here? The first equation just simply says, well, let's take a line, a spectral line, and if we set R equal to 0, then we get S nu equals SL. And that's what we talked about in the two-level atom, because we didn't want to complicate things. Now, all he's done is to say, well, a line is not the only source of emission and absorption. There's got to be something in the continuum. There always is. It might be very small. It might be a value R 10 to the minus 10 of phi, or it might be R is 10 to the minus 1 of phi. But all across the spectrum, all we're doing is we're adding up the sources, that is the number of sources per unit mean free path, and we're writing the source function in this fashion. So there's nothing new there, fundamentally, just acknowledgement that there's a background. We're gonna look at the frequency nu measured in units of the Doppler width, so that it's e to the minus nu squared is the profile we'll consider first of all. Again, the old Planck function is there, and when you look at now the generalized form of the two-level atom, remember we had the source function is epsilon b plus 1 minus epsilon j. That was our statistical equilibrium equation, the one we used before. This is just a generalization to allow for the fact that we have an extra degree of freedom in R for absorbing and emitting photons. So that's why we have an epsilon star and epsilon dagger. And now we're going to be in that equation, just to make things completely clear, we have the definition of the intensity, and there's the definition of J. And what he's going to do is use this general expression to, and you can see that velocity fields are taken care of there. You have a cos theta, you have a phi nu, if that's Doppler shifted, etc., etc. So we're all ready. We've defined the problem here. One of the, and again, I apologize in putting things here, but like it's poor style to read off a slide, but this is so beautifully written. The difficulty of solving the transfer equation is a result of the homogeneous term J, namely it's homogeneous with S, it's the same power. Mathematically, this term produces a coupling between different frequencies and angles at each depth. Remember, J is part of the source function. So we've got this the idea that we've got a coupling. Physically, this coupling is caused by scattering events during which photons, and here we're starting to talk about photons, absorbed at a certain frequency and angle, are emitted at other frequencies and in all directions. A small number of photons are emitted far out in the wings. So this is, if you're deep in the atmosphere, the core of the line is the mean free path is so small the photons can't get out. But now, where the opacity is low in the wings, they start to leak out. These photons travel large distances before they're reabsorbed. This leakage of photons in the wings leads to interactions over very large distances. The non-local behavior of the radiative field is the main cause of numerical difficulties of solving the transfer equation when the epsilons are small. Okay. Now, let's then take that seriously. And what Joran does in his talk, in case you don't know, I mean, Joran revolutionized 3 things in solar physics. This was the first one. Second one was the development of the refractor as a best instrument to observe the solar surface for a given, well, that it can outpeak reflectors with much larger apertures in terms of image quality. He developed a system for acquiring very rapid frame freezing very early on. And then he started to develop instruments and a new 1-meter solar telescope. This one is often forgotten about, but I think it's the one that will go down in history, his thesis work. So what does he do? First of all, we think about a particular depth in the atmosphere, say, where the line center optical depth of something like Lyman alpha might be 10 to the 4, say. So at the center of the line, the optical depth is 10 to the 4. Now we just move away from line center and we ask, what is the frequency where far enough out in the line, and before I get to a continuum, say, where is the point in the lines, in the wings, where photons can start to escape, right? So what this means is, it relates to what we talked about last time, which is the radiative transfer has effect of broadening the lines, and this is basically the effect that's going on. The photons in the core are trapped in an optically thick line, and they escape where the optical depth is unity. And this number, nu1, could be several Doppler widths away from line center. In contrast, an optically thin line with tau at 0 equals 0.1, say, would be just reflect the profile of the Gaussian function, the local Gaussian function. And they would emerge mostly between plus or minus 1 in Doppler units. So an optically thin line then would have a width, which is, say, a 1 unit, whereas an optically thick line is going to have a width of the square root of the log of tau. That's just from the e to the minus x squared. So it's going to be significantly broader. So we've now got a very simple understanding based upon only the line profile as to where photons we can expect them to emerge in frequency. We define a probability of escape. And we say, okay, let's do the crudest thing we can do. Let's assume that out to optical depth 1 across this line, then we can define the fraction of the line photons which escape on the left and right hand side of the line profile, so factor 2 there, integral of nu1 phi nu d nu. Couldn't be simpler. So we're just saying all those photons out in the wings have an escape probability of 1, and all of them in the core are 0. We're going to make an error around tau equals 1, but we want to see where this gets us. And this was actually, this kind of argument was developed as early as 1941 by Zanstra, and it has an analytic solution. That's for a Gaussian function. You have the complementary error function. Notice that this knows absolutely nothing about the transfer equation. All it knows about is the line profile. And there is one number at each depth for each transition which can be used to solve approximations to multi-level non-LTE transfer equations. And yet, at this point, it doesn't know anything at all about radiative transfer. It's just a statement of heuristic argument about photon escape. So this on the left is what Joran is most famous for, but the stuff on the right, I think, is some of the most insightful stuff in physics that he's ever done. I mean, in case you wonder, I really admire Joran Sharma. Okay, so what are we talking about? This is a plot of the Gaussian profile, and this just represents what I said. The shaded region is a place where there is no radiative transfer, and what that amounts to is setting J to nu, because di by d tau is J minus S. So if there's no rate of transfer, the I jet by d tau is 0. So the photons are trapped. Okay? And the probability of escape we set to 0. Now, on the other hand, in the unshaded regions, the J nu is approximately equal to the tau nu, the source function tau nu equals 1. And so it's not J equals S anymore. It's something different. And what it is it's the escape probability is the error function of X, and X is on the X-axis here, wavelength in Doppler units. Okay, so it's a one number. And I can compute that for different kinds of profiles. It's obviously very different for the Gaussian profile. This is a function again of frequency from line width. And if the source function, you imagine dropping from left to right here, you can see that this builds up different profiles, because if you do S nu equals I, the emergent intensity is S of tau equals nu, and we imagine the escape, the source function increasing it, this is going to give us different profiles. So anyway, the two void functions are plotted there, and you can see the effects of the wings. This is the effect of wing transport, and you can see that, you know, the solutions are going to depend rather sensitively. The escape probability can be different by a couple orders of magnitude, often, depending on the type of rate of transfer we have. And a couple of things ago, we talked about partial redistribution, which is what is the, you know, connection between an incoming photon and an outgoing photon as seen by the observer, not so much by the atom, but in the frame of reference of the observer and the atmosphere of the sun itself, as opposed to the atoms. Okay, so actually a redistribution function looks like this. So what does this, looks very strange, doesn't it? It's all off to one side and everything like this. So what is it? It's basically saying on the x primed axis, we absorb a for each value of x, we have a profile. So let's look at the peak one in the middle there of 0. So if we absorb a photon at 0 Doppler shift, then it's re-emitted at it has no net velocity. The photon will be re-emitted at points along that curve, so that it's going to be symmetric in frequency. Now we go to say x equals 2. So we've absorbed a profile. We've absorbed a photon at values of -2 and +2, say, and then that thing tells you how they're emitted in frequency, re-emitted back in frequency, taking into account the fact that we're moving from the frame of reference of the atom into the observer's frame, and that's why that thing is broadened and shifted. Now we go to further away, and that looks pretty symmetric. We go further away to x equals 3, say, and now you can see that the photons tend to get emitted around the same place where they are. That's the Doppler broadening. But the wings in the profiles and stuff like this start to get stretched out sideways until we get way out in the wings where they start to look symmetric again. So this kind of makes sense physically, the relationship between the incoming and outgoing photons, whereas in this figure here that I'd shown you, this is just symmetric. Sorry, the solid curves are there is no velocity shift at all accounted for here. This complete redistribution, which means that function is flat instead of peaked. Whereas it turns out in partial redistribution, you have to do some detailed calculations. And if we have time, we'll get to the end of that. Some work by friend and colleague Ken Gailey has done that analytically. But anyway, the basic point is that we have some kind of simple expression, or we can imagine developing a numerical solution for which we might fit something here for a void profile that we can use to examine the rate of transfer. And you can see that this is going to have a big effect here, because this is remembering the frequency it was emitted at and re-emitting it at that frequency, whereas this is forgetting. So this is a source function that's in complete redistribution. This is the kind of thing you get. The peak ones off center are the ones you get for partial. Okay. I'm sorry to go back to the equations again, but we do have to introduce some rate of transfer, because if we only have escape, then we'll see what the consequences of that are, and they're sort of written down here. So what is this all about? Well, we know we looked at J minus S, and we said that the emerging flux, rate of change of emerging flux with depth is J minus S. But we wrote earlier that J is lambda S. And I'm going to write that operationally as, and remember we saw some graphs, and this K just shows you what those graphs are. Again, from Kurganov's plots and others, these have these particular shapes, and it's symmetric around the local value of T, which is why we have T minus tau there, or the local value of tau, sorry. Yeah. So notice the difference between the first and second lines there. I've shifted the S outside of the integral. That's not usually a smart idea, because if S is varying with tau, in principle, we can't do that. But let's just do it, noting that the K function usually extends plus or minus 1 optical depth away from the given tau. So K is going to be pretty small when its argument gets beyond about 2, 3, 4, etc., let alone 10 to the 4. So it might be a reasonable approximation. And what it's saying is we're assuming that S varies smoothly compared with the effects of rate of transfer by shifting it outside the integral. So we end up then with an expression which looks like the left-hand side, and it's a function of line center of line center optical depth, because remember this is already integrated over angle and frequency, so this has no sub nu on it. So this is J bar actually. So what we can do is we can compute this thing, and then we can relate it heuristically to escape probabilities, because if we have the form of this thing and we take J minus S, then we can just go through the algebra. We know this is a function of the optical depth we're looking in the atmosphere, and what we see is that it's basically the escape probability. So this is just saying that this is the fraction of photons which are going up and down in the line which actually end up escaping. That's the heuristic argument, and that's what this equation sort of represents. Okay, so J minus S is, you can construct, so it would be S of K minus T minus tau minus 1, and if you put half in there to allow for the fact that half the photons aren't coming in at the surface, then you end up with an expression like this, and this is the escape probability. So at great depth, we have approximately that this is true. And this is just saying that the number of scatterings in the atmosphere is a large number, except for a small fraction, P escape, which escape. We know also that because we're looking at a 2-level atom, and so we have this expression here is the one we had before, nothing different. It's the same one that Ioannou has with his epsilon and epsilon star, etc. And now I just substitute this in here, and I get just a simple relation between S and B, which says that if epsilon is very large compared with everything else, S goes to B. So this is what we want. What we've said there is that photons don't do anything, and so it's not surprising we recover the Planck function. Now we look at the opposite case where the escape probability is very large, so it could be as much as a half at the surface, because half the photons go out and half of them go down, and epsilon is 10 to the minus 4, then we get S is about twice epsilon times B. That's not what we want. We want the square root of epsilon. So we conclude from just this very simple allowing rate of transfer to be implemented to take the escape probability, which again knows nothing about rate of transfer, it's just argument based on escape, and we put it in then into the formal transfer equation, and we make this is what we do here, and we make an approximation, identify this thing, then this first order approximation is called first order because this is a linear equation in S and P in the end, this one. We end up with the wrong answer. So escape doesn't account for the upcoming flow of photons from beneath. It just accounts for photons going out. Nevertheless, the thermalization depth agrees roughly with the detailed calculations. So a very simple calculation like this shows you roughly where the source function has to go to the Planck function. Okay, makes sense, I hope. But what about the surface value? We know that it must look like this, and there are some beautiful papers written in the 70s and 80s, and we end up with a solution, which I'll guide you to now, from Yaron Sharma, which does, in fact, with a very simple modification of this, give you the right surface value, which means that over the whole atmosphere, we've got the bottom point understood as the thermalization depth, and then at the surface, we've got the top point understood in terms of the square root of epsilon. So we fixed S at 2 points. So we're going to know what the source function looks like if indeed we can reproduce this epsilon b. So basically what he does is, and this is where the physical insight is simple, but so profound that you bash yourself on the head saying, why didn't I think about this? This is genius here. So when in the line core, you say, well, I is about S. That means that J minus S is 0. It means no flux, no transport. That's what we assumed. And so we have then, for very thick optical depths, so we just compute the line profile, use the abundances and the line profile to compute what the optical depth at each frequency is. And for those in the core for which the optical depth is much bigger than 1, equation 8 applies. That's the detailed balance. That's the on-the-spot approximation. That's the zero escape probability. Now, for when we above the atmosphere, very low optical depths, and for outgoing rays, we use the Eddington-Barbier relation. Okay, we talked about that. It's a simple A plus B times tau assumption, and we end up with the intensity is going to be on the order of the source function at tau equals 1. Nothing difficult about that. And now, I've covered up the mu is minus it. For incoming radiation, we set that to 0. So now we've got everything we need to do to compute J, because we've specified, and we can use a two-stream approximation, outward going and inward, to compute J, if we like, just a straight average of the two. So but in the wings of the line, where it's really optically thin, sorry. Now we need to do something. We don't know what the source function is in the wings of the line, valid above throughout the atmosphere yet. So we have in extending the from 7 to 8 into 14, what we're doing is we're allowing some dependence of S on the optical depth scale instead of just assigning it with a 1-point quadrature, which is what we did with equation 8. Okay, and what we're going to do is we're going to try and do slightly better than equation 8 here in the wings of the line in order to allow for rate of transfer across the region, the entire region of the escape probability in terms of frequency space. And what, just with a tiny bit of algebra, which I'm not bothering to show, you end up with the J nu is about half of the source function at some new number, which, when you look at the algebra, comes out to be a number, for whatever reason, that looks like this. So if you have psi is very large and r is very small, then that's a small optical depth. So now we're looking at the stuff that's kind of incoming from above and allowing it to vary. And so what do? We just sum up the expression there for in the wings, 17, We use that in the right-hand side of bottom 19, and we use the previous approximation for the line core. Okay, so this is, and his statement is just so beautiful here. So what he's actually constructed, and if you're interested, I would read the paper, is something that in which the wing integral in this equation contains the long-range interactions resulting from the efficient transfer radiation by wing photons. Again, we're focusing on photons. Note also that the upper boundary condition, namely the optically thin end, is included in the wing integral. So the above approximation indeed contains the basic mechanisms of radiative transport in spectral lines. So the argument here is that a heuristic approximation allows him to split between a core and a wing. The core is saturated, there's no transport. The wing is where the transport's going on, and he's looking at the surface down and the bottom up. So there's some hope that we can actually get what we need from this thing. And here is his expressions where he's basically set the continuum opacity to 0 for us conveniently, because then, well, we're familiar with what this is. The top equation is now an approximation to the full transfer equation, but it doesn't contain any intensities in it. That's really what we're trying to do. We're relating S. We have an implicit equation here for S in terms of epsilon primed and B. And remember, there's only one epsilon now because we got rid of one of them, the continuum optical depth. And so what we end up with is this equation 24, which is reproduced on the right again. And noting the normalization, integral of phi nu d nu is 1 over frequencies from 0 to infinity. You end up with this expression here. And so the expression in terms of the destruction probability epsilon, that couples the plasma and the photons to now what look like two escape probabilities, one of which has SL of tau primed under the integral. The first one of those terms is just an escape probability, okay? This is different from what we'd done before because we've got a more sophisticated treatment. And there again is the escape probability. And we end up with an equation that looks like the above. So what he's done here, mostly rate of transfer is done over optical depth. But now you can consider making a one-to-one relationship between optical depth and escape probability, which is basically, if these are monotonic, then you can say the x-axis is proportional to optical depth, and the escape probability is a monotonic function of that. So we can go forward and use the escape probability now as the independent variable here. You can imagine what we started with was dh by d tau equals j minus s. So we've got a tau and we've got an intensity in there. Basically, we've replaced the tau by the p here because there's a one-to-one correspondence for any given profile. And what we've done then is to say, well, look, we can now write it in terms of escape probabilities, which know nothing about the intensities at all. So here, what we've managed to do is to capture the essence of rate of transfer from the transfer equation, replace the formal integrals for lambdas with these heuristic arguments in terms of escape of photons. And we end up with an expression in which we've got a dependence of the source function on escape probabilities. That's like ds by, on the bottom there, ds by d tau. That's the equivalent expression here. So it's a transfer equation, except now it's all written in terms of escape probabilities. So if we look at the top equation, he also does this wonderful thing where he explains to you simply what the hell is actually going on. This has a simple interpretation. The number of photons created or destroyed at depth tau, that's epsilon prime times that term on the left, is balanced by leakage of photons in the wings. That's the first term on the right. And it is also the second term. So what's going on is there's a local part of this term implicit in this now. since the leakage is isotropic, that's the left term, while the inflow comes only from below, the former flux tends to be twice as large as the latter, which is the reason why SL usually is smaller than B. So now we know the reason why the source function drops with depth, at least in terms of a simple heuristic model. Okay, so what do we do next? Well, he says, here is the resulting equation. If we just differentiate that equation, we end up with that expression there. This says that the rate of change of SL with probability of escape or with depth is minus SL plus some derivatives with respect to optical depth of B and epsilon. He then says, well, let's just make a further approximation and see where it gets us. We're going to make some mistakes if we have variation in depth of, say, the temperature or the collisional destruction probability with depth. But something like the chromosphere, the temperature is pretty constant. I mean, it's not really, because in the UV, the Planck function steeply depends on temperature, so it's not quite right. So you're going to make some mistakes. But generally speaking, what you can do is say, well, let's assume we have a nearly isothermal atmosphere, and let's not let the densities change too much in it. And the chromosphere, oddly enough, even though it spans many scale heights, the electron density is roughly constant across that. And so what that means is that all the collisions, the destruction by the impact of electrons with the atoms and collisional removal of the excited states, etc., those don't vary much with depth either. So amazingly enough, you can trash those two right-hand terms, and then you end up with ds by dp equals minus SL divided by the epsilon prime plus 2pe, and that gives you a square root dependence. We've trashed those two, and we end up with an expression like this. I will just read from him. The solution is remarkable since it gives the correct thermalization depth, SL go to P, when PE is on the order, where the PE is on the order of epsilon primed, or 2PE is, and the exact value for the source function at the surface. So we had an equation which was linear and before, which was wrong. So in this so-called second escape probability, this is what this means here. We've got S depending on, or S squared depending on P, essentially, from this equation. Then we end up with something that we can use because it has the correct values at 0 and at infinite optical depth. So we've managed to treat radiative transfer, albeit with all these different approximations, without even really dealing with the radiative transfer, just with escape probabilities and the statistical equilibrium equations. I think that's remarkable. If you're not convinced by how good this is log SL, so there are some errors here on the order of 0.05, 0.1 or something. But this is comparing with numerical calculations, and without doing radiative transfer, you can get radiative transfer solutions just on the basis of heuristic arguments for both lines which are in the solid dots are the Lorentzian or Voigt profiles, and the open ones are the Doppler profiles. And there's the dependence of the source functions from, essentially no work on the computer. So what this has done, and I think we'll stop here this week to consolidate it later next week. But to summarize, what's happened here is that Sharma has used his intuition, various physical approximations for better or worse, but nevertheless has come up with a way in which the actual rate of transfer can be described in terms of photon escape, both in a local, that's the first order approximation, and a non-local formalism based upon things like the assumption of core saturation, no transfer at all in the core, escape in the wings, And he's done pretty darn well over orders of magnitude in optical depth and source function. So this is an enormous step forward. The results were known before, but the explanation and then the second part of the paper, which I'm not going to talk about, if you can do this analytically, imagine getting yourself a lambda star operator. Remember we talked about getting an approximate operator at each point in the transfer equation and then iterating. This is what we talked about with the Arley methods. This fits exactly into that kind of idea. Very early on, George Rybicki in 1971 said, let's just ignore all the transfer where the photons are optically thick. We won't even bother putting them in the equations. We'll just integrate over the thin parts. And came up with a scheme that was rather efficient and accurate for solving relative transfer equations. That's just by canceling out those terms in, essentially those terms in the equation for which Bj bar equals Bj bar, the upward going and the downward going photons, they just cancel out completely. So what you do is you write your statistical equilibrium equations down, which is just a matrix equation for solving for the populations of the atoms. And then for each frequency in each line, you basically just don't calculate anything. You set those Bj bar terms to 0, and you only do transfer in the wings. And if you use something like a Fourier solution, once you've built up your rates and you've got your number densities, you've got everything you can use a formal solution, a version of the lambda operator, applied to the wings only, and that converges without, you don't need any linearization or anything for a two-level atom. You would need it for a multi-level atom, and that converges very quickly. And then Sharma, in the latter part of this paper, and Ed Carlson and Sharma in 1986, they developed the full thing for multi-level non-LTE, including these ideas, not explicitly including escape probabilities. So they didn't, for instance, start with a second order escape probability solution like this for each transition and then iterate from there. They came up with a way of computing the lambda operator with containing some of this physics and then iterating to Newton-Raphson to get solutions. So I'm going to skip over this. But what I will talk about next week is, in general, if we had a multi-level atom in which we had an equation like that, there's another way to do things. And you can say, well, maybe it's thick everywhere pretty much before continuum comes in and takes over the rate of transfer so that we can set this term redshift detailed balance. We can just cancel that out completely out of the equation with no wing photons. Well, what use would be of that? Well, think about something like hydrogen atom and think about the optical depth might be in the Lyman continuum in the chromosphere. It's 10 to the 4, 10 to the 6, something like this. Gets to be optically thin only at the last scale height at the top where the transition region appears. What that means is you can pretty much use for all the Lyman continuum, and remember it's EUV photons down at line 11 in a temperature of 7,000 K. There's almost no photons, almost no J there anyway. So what people like Gene Averett and people did in the early days of building models, they actually formally set redshift detailed balance. And even if you go back to Menzel in the 1930s, this is called, for things like planetary nebulae, they were interested in modeling H alpha and what have you, given the new results from quantum mechanics and the work in the late 20s from Payne-Koboshkin about the abundances. They were ready to do these sort of non-LTE calculations. But they realized that at those depths, we didn't actually need to include that. So what they did was they basically just said, well, let's trash those terms. And we end up with an equation that looks like N2A21 plus C21 is N1C12 for that particular transition. It's also true for all transitions below the thermalization depth, because then the C21 and the photon transport has been taken care of by this lack of an escape. And this looks now like the optically thin case. So this, if you've ever looked at the literature for nebulae or even applied to the solar atmosphere, this is called case B, where what you do is you get rid of all those photons. And it's, I don't know, it sounds a bit strange to call it case B, but that's historically what it's became known as. And then finally, Rybic's core saturation method is exactly just detailed balance, but instead of getting rid of all the terms, you only include those at the frequencies where photons escape locally. And I think I'll stop there. Thank you, Sasha. That helps. Any questions or anything? Okay, so thanks for listening. Next week, I will get into try and reinforce these ideas a bit with extending it to a little bit of partial redistribution, and then talking about some more familiar kind of, just to increase your familiarity and to show you some applications. And as I said, there isn't much left here, so we'll have plenty of time to try and do this. But I hope that was at least somewhat clear. It hopefully will become clearer again as we go forward. It's really a neat way of understanding photons moving around in boxes in space and frequency. It's and that is, after all, sort of what's going on physically. So this maybe is a case where the classical atmosphere limit of I's and J's and S's, as opposed to photons, has led to a formal solution, which is difficult to understand. It was only till we really put it in terms of, motions of particles and transport that it became very clear. So, all right, on that, I think I'll hang up, and I have a meeting to go to. All right. Thanks.